we go. All right. So before we look at our test from yesterday, I want to have a chance to, before Allie goes and does hers, have a chance to talk about the pre-response stuff a little bit. Now I know that's next week. So tomorrow we have our calculator multiple choice one, and you're going to have some time today to work on this stuff here. And then I do have one new couple page thing on classifying critical points. Okay, so it's really important. You know, the whole idea of max and mins, local max min, global max min, that idea, that comes up a lot in a lot of types of questions. Pre-response especially is kind of what I'm thinking about here as we look to next week, Monday and Tuesday being those. But we also are going to get started on our group paper too. And so one of the things we'll do after we talk about this and then we go over the test is have you on a piece of paper write down the names of about 3 or 4 other people you wouldn't mind working with, or 5 or 6, or if you truly want to work with anybody, you could write that down. Or if you're like, you know, please don't put me in a group with so and so. You know, I just can't work with that person. I mean, I guess you could put that down too. And then I'll make up the groups and you know, but try to get you in the group with at least one other person that you would wanted to be in with, or thought you would want to be in with. And so groups are like 3 or 4, and so that's for our group papers that we will get started on. I'm actually going to talk about those tomorrow after the quiz. Thursday was kind of going to be work time for the, you know, kind of on the packets of that, which you still can do that. But I thought, well, we're, you know, kind of a little short on time maybe, so maybe that would be a good day to work on the group paper too. Now, some people are going to be gone for track, I know, so your group may have to get started with you a little bit, or they can work on packaging, do that on Friday. Friday's going to be work time on that as well. Monday and Tuesday, we do the free response. They're each 45 minutes, so you'll have, you know, another 30 to 40 minutes where you can be working after that as a group as well. Okay. It's not going to be due till that next Monday. I mean, so what is that, like the 14th or something actually due? But what, you know, like I said, we'll have some a little bit of other stuff we'll be working on too, but not a lot of things. So anyway, all right. So let's go through this. So what I've tried to do here, you don't need to write this down. I've got this on our class website. Oops. I've got this on our class website here under the documents section. Right here at the top, it says AP Free Response Review Topics 2. Okay. And that's a PDF that you can look at, especially those of you taking the AP test, but as you look towards the free response stuff next week. So I've got that there as a PDF. So the 2017 free response questions is one that I handed back to you. You guys did, I handed back to you. And so what I've tried to do is highlight the major topics that are covered and just maybe touch on a few quick things about that. And some of this could apply to the multiple choice questions too. But one big thing is chart stuff. 2017 number 3 was all about that. One thing I want to remind you of, remember when you're doing a free response, we may talk about some of this on Friday again, but just in case we don't, you know, when you're talking about a local max, local min, you got to say in a free response, hey, that because F prime changes positive to negative, F goes increasing, decreasing. You know, you can't just use your number line, you know, to take care of that. So you've got to write those things out. You know, if you're doing inflection point, F double prime changes sign, so therefore F changes concavity. Or don't forget that inflection point is when F prime has a local max or min, right? Because if F double prime is positive and negative, that means F prime goes up then down. So that's a local max or local min, and that means a change in concavity too. So some of those things we haven't done for a long time. We've been doing it as we go through the package, but we haven't always got to talk about it a whole lot. Global max min, remember we did a list of candidates. These are the 3 different sets of candidates we have. Sometimes you only have one candidate, and so like if you didn't have endpoints and there's only one place a derivative is 0, you could use a number line and use the word always. You know, since F prime is always positive before and always negative after, that means F is always increasing and always decreasing. That would be a global max as well as a local max. So we talked about that. Okay, so that's one big thing. We talked a lot about area functions, you know, the area from 1 to x. We said when we see that, we think antiderivative, antiderivative. So a way to show something's an antiderivative is to write this down, that g prime would be little f. Because a lot of times what they do is they give you a graph of little f, but they ask you a bunch of questions about g. So that's something we want to make sure we understand. Remember the Shanghai or the Luke Skywalker problem? It was when we had a tangent line, but we didn't know where it touched, like this. Okay, well, what could we do? Well, we do two different slopes. We could do 4 minus y and 2 minus x, do the slope between those 2 points, and then we could do the derivative of this curve, and then we could set those equal to each other, and we could find that point. That was Luke Skywalker.
We do it like that after we go through this.
Yeah, at some point, maybe, or
Like,
I could show you one or something. Yeah, for sure. Okay. And then we had our average formulas. Average rate of change of f is just slope between 2 points. If it's average value of f, then it's this formula here, right? And we set those up, okay? And then we do the integral however we can do the integral. Maybe it's by doing fundamental theorem part 2, big F of b minus big F of a. Maybe we just type it in a calculator. Maybe it's a table of data and we have to do a Riemann sum. We're going to talk about that here in a second. Related rate problems, you know, that's when you have your rates of change, x prime, r prime, h prime, b prime, you know, whatever the case may be. Riemann and trapezoid sums. So we did a packet on tables of data. It's been a while. The thing I wanted to talk about here on this is set up the integral first. When you do a Riemann sum, you're doing it for an integral. Now, sometimes you get a problem where it says, find the average value using a left Riemann sum. It's like, how do I do average value with Riemann sum? Well, you don't do average value with Riemann sum. You do an integral with a Riemann sum. You set up your average value formula, and then to do the integral, you do a Riemann sum. How do you do a volume with a Riemann sum? You don't. You set up an integral for the volume, and then you do the Riemann sum. For example, 2017 1A. I'll just pull that up here real quick. Here's 2017 free response number 1A. Now, I think we've already talked about it. Now, what you have here is a table of data with square feet here. Okay, square feet. Now, the problem here in number 1 says use a left Riemann sum with 3 subintervals to get the volume of the tank. Well, since this is the area of the slices, the cross sections of the tank, it says the area of the cross sections. We all know that the formula for volume is to do your area. This would be A of H. You just put area in here. Well, since area is what they gave you in the table, that's fine. So you turn out and you just do 50.3, what they say to do a left. So it'd be 50.3 times how much? 2. And then you would add on 14.4 times 3. And then you would do 6.5 times 5. Now, why does that give you volume? Well, this is square feet and this is feet, so that would give you cubic feet, so that would be volume. So that wasn't really that hard, but it was a little different. Some people got confused by that last year, but that's your Riemann sum. Now, usually we did a Riemann sum to do area. And why was it area? Well, this was just the height of some function, so it was the height times width, height times width, height times width. That was area. Here's how I've seen this problem given, though, that really gets confusing. And it shouldn't be that confusing. Is where, what if I told you that these numbers down here wasn't the area of the cross sections, it was the radius of the cross sections. Now what would you do to get volume? You would have to square this and do what else? Now, we've hardly ever had a problem where we've done a Riemann sum and we had to have a pi in there and an r squared. Why are we doing it here? Here's why. Because when we set up, and this is why I said that in those notes, to set up your integral first. Because if it says to find the volume of the tank, and we're given a function for the radius, that's like when we do our strip and we figure out what r is. So we would set up pi r squared from 0 to 10, and then we would do a Riemann sum to do this integral. So what we would have to do is do pi r squared times our width, pi r squared times our width, pi r squared times our width. Does that make sense? I mean, so this is a different looking Riemann sum than we're used to seeing. Usually we just put F on whatever, we just do the Y value times the width, Y value times the width. Well, that's because we're usually doing area. Here, they gave you area times the width, gave you volume. But what if they gave you radius? You would have to actually do that. Okay, so I guess what I'm saying is, in these notes, is when you're asked to do a Riemann or trapezoid sum, usually it is just an area problem. So it's pretty straightforward and easy. But that could happen too, and they came close to doing it last year in the 2017. Okay, all right, so anyway. Big deal that we talked about when they give you the integral of a rate, that's the amount of change. It was 2017, number 2. It was this problem with the bananas. Here's the rate that they're taking bananas off the table. Customers are taking bananas off the table, pounds per hour. Then the employees start putting bananas on in pounds per hour. You do the integral of that. That tells you how many pounds of bananas have went on, or how many pounds of bananas have come off, the net amount of change. What if you wanted to know how many pounds of bananas were on the table at a certain time? What would you have to take into consideration? How many, the initial condition, how many pounds were there to start? Because when customers start taking off, you have to take that initial amount and then minus what that integral would be. And then when employees start putting them on, you would have to add that back on. But you would have to know how many pounds were there to start, which it says there was 50. So you have to take into account that initial condition. Okay, we did differential equations, 2017, number 4. We verified, we did slope fields, we did separation of variables. Tangent lines, this is your formula for tangent line. The way you get the slope normally is to do a derivative, or maybe if there's a differential equation you can plug into or something. Another term that's often used with tangent lines is linear approximation. That's when they tell you to do the tangent line at, say, at 2. But then they ask you to then use that to approximate the function at 2.2. Well, that's because the tangent line and the function are pretty close together right around this point. So you can find the tangent line at 2 and then plug a 2.2 into that equation, the line equation, and then that gives you a point that's pretty close to the y value on the actual function. That's called linear approximation. Okay, so if you see something like that. Okay, motion problems, there's all kinds of different motion problems out there. 2017, number 5 was an example of one. Total distance traveled, remember we do the integral of the absolute value of velocity. Speed is equal to the absolute value of velocity. We talked about how something is speeding up when the velocity and acceleration are the same sign. Speeding up when the velocity and acceleration are the same sign. Slowing down when they're opposite signs. Okay, then we had the theorems, remember? Mean value theorem, the slope at the endpoint is the same as the slope in between at some point. Function has to be differentiable for that to be the case. Differentiable, remember, means smooth. Not only is it connected, but it's nice and smooth too, no sharp points. Intermediate value theorem just says between the endpoints it hits all the y values. So between here and here it's going to hit all those y values. And it has to be continuous for that to happen. And continuous, remember, just means connected, no gaps or breaks or holes or anything. Okay? Talked about piecewise functions. How will this piecewise function not have a break in it? How will it be continuous? Well, they have to have the same output at 2. So you take 2, put it in for x, take 2, put it in for x here, set them equal to each other. They have to have the same output. To be differentiable, to be smooth, they have to now be connected. They have to have the same slope. So you plug in a 2, find out where they have the same output, and do the derivatives of these, and plug in a 2. And then those have to be equal as well. Okay, so for example, in this case here, we have 2 variables. We'd have to know some other information, but we could plug in and we could figure that out. Okay, well, actually, if you plug a 2 into here, you'd have 12 plus 2b. And then if you plug a 2 into here, you'd have 2m plus 3, right? And so we could get 2b is equal to 2m, what's that, minus 9. B would equal m minus 9 halves. So we would know that much. Then we can do, for it to be differentiable, we can do the derivative. So this would be 6x plus b. So if we put a 2 into there, that'd be 12 plus b. And then do the derivative of this, that'd just be m. That's got to equal m. Well, now we can substitute, right? We have 12 plus b equals m. So now we can take this, and we can just put that right in there for that m. So we would get b equals 12 plus B. Oh, this didn't work very well. I just made this problem up earlier. Isn't it good? As I just screwed this problem, we have someone here to give us a photograph again. It's at least you can't be video. Oh, wait a minute, but I'm recording. No, this is on YouTube. All right, no, that's good. All right, anyway, well, why is this not working out very nice? What's happening? The bees are going to drop out, right? So in other words, there isn't going to be a place evidently where this is going to happen. But anyway, that's what it would look like. It would work out. So you put a 2 in for x, set them equal to each other. Do the derivatives, put a 2 in for x, set them equal to each other. And then you can find what b is. Once you find what b is, plug it in, you can find what m is, right? And away you go. So that's kind of what something like that would look like. All right? Those show up in the multiple choice a lot sometimes too. All right. So anyway, though I wanted to make sure I'd gotten through this. Now, like Cody said, we can pull up. I've got some old free responses. We've done several of those packets, but as we get closer to the test, and then a few of you are taking the AP test in a couple of weeks here, so make sure we we kind of just stay up to date on these things, ready to go. Okay. All right.